When we think about the digital world, we usually conceptualize it as entirely weightless, like it's just floating around in the ether somewhere.
Right. It really is the ultimate magic trick of the last 40 years or so. We literally call it the cloud. We
Exactly.
use this language that makes our data, our algorithms, our whole global communication network sound like it just exists in this invisible, frictionless vacuum.
Yeah, you send an email or stream a movie or ask an AI a question, and it feels instantaneous. It doesn't have gravity. It doesn't sweat. It's just clean.
Oh, totally. But we've been living in this incredibly comfortable software bubble, and, well, that illusion is crashing hard into the real world right now.
Pushing very hard.
Yeah, because eventually you hit the limits of physics, you hit the absolute constraints of thermodynamics, and suddenly that weightless cloud smashes right into heavy physical infrastructure.
And that is exactly why we're here. Welcome to the deep dive. We've been living in this illusion of a weightless digital world, but today we are unpacking a sweeping, just really visionary piece of writing that says this illusion is completely over.
Yeah, we are plunging headfirst into an era of sovereign, infrastructure-heavy, deep tech.
The source for our mission today is a 2026 post by Paramendra, and it's titled Netizen 15 Technology Clusters.
And the author lays out this core thesis that we are witnessing a massive, unprecedented wave of convergence. Like, we aren't just looking at software getting a little smarter or batteries getting slightly more efficient.
Right, it's way bigger than that.
It's a moment where the lines between software, heavy manufacturing, global energy grids, and even human biology are just fundamentally dissolving.
And what's wild to me is the framing of all this. The source doesn't just treat this as some, basic hardware upgrade. It frames this convergence as the dawn of an age of abundance.
Yeah, that's a huge term.
It is. The text even notes that this kind of civilizational shift was prophesied in ancient scriptures thousands of years ago. It's a massive claim to wrap your head around.
It really is.
But I promise you, by the time we finish this conversation today, you are going to understand exactly how these converging forces are actively rewiring the physical world right outside your window.
So to understand how a claim like an age of abundance could actually physically manifest, you have to look at the underlying engine driving all of this.
The intelligence.
Exactly. It starts with the fundamental evolution of digital intelligence itself. I mean, the early wave of generative AI that caught everyone's attention was essentially a highly advanced conversational parlor trick.
Like a really smart chatbot.
Right. It was a prompt and response dynamic. You typed a question, it gave you an answer.
But you, the human, you were still the central processing unit of the actual project, right?
Absolutely. If you were trying to launch a marketing campaign or write this complex financial report, you were the one taking the AI's output, reading it, pasting it into a different app.
Realizing it messed up a number somewhere.
Yeah, realizing there was an error and then prompting the AI again to fix it. You were the project manager holding everything together with duct tape.
But the text says that entire paradigm is shifting, right, toward agentic AI and multi-agent systems.
Yes. We are moving from passive assistance to autonomous, goal-oriented execution. So an AI agent isn't just a chatbot waiting for you to say something.
What is it then?
It's a system equipped with memory, access to real digital tools, and the ability to reason through a sequence of actions. You give it a high-level objective, and it formulates a plan.
So it actually navigates its own environment.
Exactly. It executes code, and crucially, it course corrects when it hits an obstacle, without you holding its hand.
But the real commercial scaling here, what the text points to, isn't just one omnipotent super AI trying to do every single job. It's the multi-agent system, or MAS.
Right. The division of labor is what actually makes this viable for a real enterprise.
Because the massive models are just too clunky.
Yeah. Massive, monolithic models are incredibly expensive to run, and they get confused easily when juggling too many competing context windows. And MAS solves this by deploying a distributed web of highly specialized, smaller agents.
The source illustrates this beautifully with software development.
Yeah.
You don't have a single AI trying to write an entire app by itself.
Right, that would be a mess.
Instead, you deploy a system where, like, a product manager agent first gathers the requirements and drafts a spec document,
Then it autonomously hands that context over to an architect agent.
which designs the database schema.
Exactly. And then a developer agent actually rates the syntax, while a totally distinct security agent continuously audits that code for vulnerabilities.
And they literally negotiate with each other, right?
Yeah.
That's the craziest part to me.
Yeah, they do. If the developer agent tries to implement a feature that uses some unencrypted protocol, The security agent will flag it, reject the commit, and send it back.
That's like a real team.
But all of this happens in milliseconds, iteratively, completely, without a human needing to referee the argument.
My analogy for this whole transition, the old conversational AI, was like a wildly enthusiastic, jack of all trades intern.
Ah, yeah, exactly.
They confidently guess answers. Sometimes they get it totally wrong, but they're generally helpful if you sit right next to them and watch them.
Whereas a multi-agent system is like a highly coordinated corporate department of seasoned professionals who know exactly how to stay in their lane.
Right, and that specialization is the defining characteristic of this new era, which connects perfectly to the rise of domain-specific language models, or DSLMs.
Yeah, because the broader tech narrative has been totally obsessed with these trillion-parameter behemoths, the ones that know everything from, 14th century French poetry to the rules of baseball.
But the text argues that for deep tech and real enterprise work, that broad knowledge is actively detrimental.
It is a massive liability. Large general models carry severe compute costs, really complex data privacy hurdles, and of course the persistent issue of hallucinations.
Right, because if you're using AI to brainstorm ideas for a sci-fi novel, a hallucination is just a fun, creative spark.
Exactly. But if you are running an aerospace engineering firm or diagnosing a real patient in a hospital, a hallucination is catastrophic.
Which is the exact problem DSLM solve.
Precisely. Instead of scraping the entire internet, you train a smaller, highly optimized model exclusively on specialized, curated industry data.
You just put blinders on it.
You narrow the parameters entirely. The text highlights medical applications for this. A healthcare-focused DSLM is trained purely on verified clinical trials, complex pharmacology, human anatomy.
So because it isn't burdened with trying to understand internet slang or global history, it can parse incredibly dense, chaotic patient records with near-perfect fidelity.
Right. The mechanism here is about reducing the probabilistic noise. When a general model generates a word, it's selecting from a vast distribution of all human language.
But a DSLM's probability distribution is hyper-constrained to its specific domain.
Exactly. So it runs at a fraction of the inference cost, uses way less electricity, and delivers strict regulatory compliance because its outputs are mathematically bounded by its specialized training.
Wait, I totally understand the efficiency and the safety argument there, but aren't we losing something huge?
Like what?
Well, if we shrink these models down and make them hyper-focused only on legal text or only on oncology, do we lose the serendipitous creativity that made the big general models so impressive to begin with? I mean, innovation is almost always about connecting two totally unrelated fields, right?
That is a great point, and that tension is exactly why both paradigms will continue to exist, but for entirely different functions.
Okay, how so?
Massive general models will remain the ultimate brainstorming and lateral thinking tools. They are your strategists.
Got it.
But for operational execution, like executing a high-frequency trade, auditing a contract, or controlling an autonomous vehicle, creativity is the enemy.
You definitely do not want a creative pharmacist.
Exactly. You want absolute precision. So the overarching strategy remains broad, but the execution becomes surgically narrow through these DSLMs.
That distinction makes perfect sense. Okay, so we have this hyper-capable, specialized digital intelligence. But for these multi-agent systems to actually execute complex tasks, they need a way to build and manipulate the software environment around them.
Right, which brings us to a massive paradigm shift in how software itself is created. The text highlights AI-native software development platforms.
And we are looking at what the source says is the most significant abstraction in computer science since the shift from assembly language to high-level coding languages like C or Python.
It introduces this concept called vibe coding.
I love that term so much, vibe coding. But what is the actual mechanism beneath that? Because, we've had AI autocomplete in our code editors for a few years now.
Right, but this is fundamentally different than just an AI finishing your line of syntax. Autocomplete is reactive. AI native development platforms are entirely generative and contextually aware of the complete systemic state of an enterprise.
So they see the big picture.
Yes. These platforms ingest an organization's entire existing code base, all its security parameters, its API documentation, its server architecture, everything.
Meaning a human developer is no longer sitting there typing out syntax line by line.
Exactly. They focus purely on the systemic logic. You describe the architecture, the user experience, and the data flow in plain English.
And the AI generates the syntax, builds the testing suites, spins up the virtual environments, and handles the deployment.
It's like shifting from being the bricklayer who meticulously places mortar on every single brick to being the chief architect of the skyscraper.
You define the structural integrity and the aesthetic, and the building just effectively assembles itself.
And the platform continuously monitors the code base, refactoring legacy code in the background to ensure it runs optimally on modern hardware without you ever having to manually untangle spaghetti code.
The implications for business velocity are just staggering. The text notes that this completely decouples an organization's innovation speed from the raw headcount of its engineering department.
Because small, nimble teams or even non-technical domain experts can build and ship complex, secure enterprise applications in days instead of quarters.
But wait, if non-technical innovators can build enterprise apps at machine speed, does traditional coding become an obsolete skill? It forces a brutal redefinition of what it means to be a software engineer for you and me.
It really does. The raw mechanical act of typing programming syntax is rapidly becoming obsolete, much like knowing how to use a slide rule became obsolete when the calculator arrived.
Right, so if the machine speaks our language perfectly, the value shifts entirely to your ability to think in systems.
The computer science degree doesn't die, it just evolves into pure systems architecture. You have to know what to tell the machine to build, and you have to understand the logic of how data should flow securely.
Okay, so this rapid AI-generated software ecosystem acts as the foundation for the next massive leap. Because up until this point in our conversation, everything is still trapped in the cloud.
It's still confined to screens and servers.
Exactly. The real convergence happens when this intelligence bleeds into the physical realm, which takes us to physical AI and robotics.
Specifically, the text talks about polyfunctional and humanoid robotics.
Because for decades, when we talked about industrial robotics, we basically meant a massive, rigid mechanical arm bolted to a factory floor.
Right, programmed to do one hyper-specific millimeter movement millions of times. It was blind, dumb repetition.
If a car chassis on the assembly line was a quarter-inch out of alignment, the robotic arm would just smash a bolt right through the wrong piece of metal.
Yeah, it had zero spatial awareness or adaptability. But today, physical AI has upended that paradigm using robotics foundation models.
Which are essentially massive neural networks trained on vast data sets of real-world physics and spatial interaction.
Exactly. Machines can now perceive their environment, reason about obstacles, and adapt their movements in real time.
And the physical manifestation of this that the source really highlights is the bipedal humanoid robot.
Now, from a pure engineering standpoint, humanoids are incredibly difficult to build.
Oh, I'm sure.
Balancing a heavy torso on two legs while manipulating objects requires solving insanely complex dynamic balancing equations.
Which is why the tech world mocked humanoids for years, right? The argument was always, why bother? Wheels or tank treads are infinitely more stable and energy efficient.
So why are humanoids suddenly winning the arms race in physical AI?
Yeah, why?
It comes down to the economics of infrastructure. Our entire global civilization, staircases, door handles, the height of a kitchen counter, the width of a warehouse aisle, the pedals in a vehicle, all of it was explicitly designed by humans for the biomechanics of humans.
Oh, wow. So if you build a highly efficient robot with treads and a low center of gravity, it literally can't open a standard door or walk up a flight of stairs.
Exactly. To integrate a non-humanoid robot into a hospital or a factory, you have to spend hundreds of millions of dollars retrofitting your physical infrastructure to accommodate the machine.
Building ramps, widening aisles, redesigning tools.
Right. It turns out it is significantly cheaper to throw massive compute power at solving the physics of bipedal walking than it is to rebuild the physical world.
That makes total sense. You just drop a humanoid into an environment, and the environment is already optimized for its form factor.
It can drive a standard forklift, walk up the stairs to the manager's office, and open a standard filing cabinet. The versatility is just unmatched.
Okay, so as these polyfunctional robots lead the labs and enter logistics warehouses and healthcare facilities, we are seeing AI physically manifest in human spaces.
But giving AI a presence isn't just about robots walking around. It's also about embedding AI into the frictionless flow of human interaction.
Which is where the text introduces real-time simultaneous translation hardware.
For global business or diplomacy, this is an absolute game changer.
I mean, we've had translation apps on our phones for years, but the source correctly identifies them as a massive point of friction.
Because you have to break eye contact, hold a piece of glass between you and the other person, wait for them to speak, wait for the cloud server to process it.
Play the audio back. It completely destroys the natural rhythm and emotional cadence of human conversation. It introduces a severe cognitive lag.
Right, and the breakthrough, the text outlines, relies on specialized hardware, think earbuds and smart glasses equipped with tiny, highly directional microphones.
But the real magic is the localized edge computing. They run neural acoustic networks directly on the chip in your ear.
The data isn't pinging a server in a data center hundreds of miles away.
So there's no lag.
No, the translation model is compressed and optimized to run locally. When someone speaks to you in a foreign language, the hardware captures the audio, bypasses the text translation step entirely, processes the latent acoustic meaning, and streams the translated audio into your ear with sub-second latency.
It happens bidirectionally, almost instantly. It preserves the natural conversational timing.
You maintain voice inflection and, crucially, eye contact.
The AI is basically acting as an invisible intermediary right there in the room with you, fundamentally altering how we experience global travel and international negotiation.
And this concept of the technology becoming invisible is the core philosophy of the next cluster the author talks about: ambient intelligence, or AMI, and smart environments.
Because for the last 15 years, technology has relentlessly demanded our attention. The smartphone paradigm forces us to pull ourselves out of the physical world and stare down at a glowing rectangle.
Ambient intelligence is the total inversion of that. It is technology that disappears into the architecture.
It relies on vast networks of context-aware sensors running low-power edge AI. The space itself detects who is present, understands the context of what is happening, and responds autonomously.
The source uses the example of a modern hospital. In an AMI-equipped facility, the intelligence is constantly monitoring a patient's room.
But it's not like a security camera feeding footage to a bored guard at a desk, right?
Yeah. No, it's an AI processing, telemetry, data gate analysis, weight distribution on the bed, micro-movements. It can predict and prevent a patient fall before the patient even shifts their weight fully.
Or it automatically documents complex clinical notes just by analyzing the background audio of the doctor-patient consultation.
Exactly. The doctor never has to touch a keyboard. They just talk to the patient.
In industrial or residential settings, the ambient system is continuously optimizing the energy grid, adjusting ventilation based on the number of bodies in a room, managing logistics completely in the background.
The environment just anticipates the human need.
Okay, wait. I hear the efficiency argument there, but aren't we losing something huge?
In what sense?
Well, the idea of tech disappearing into the background sounds incredibly convenient, but also deeply unsettling. If an AMI system is invisibly managing our homes, predicting our movements in a hospital, listening to our most private medical conversations,
Yeah, I see where you're going.
doesn't the invisibility of it completely rob us of our agency? How do we know exactly what it's listening to or deciding? When the screen disappears, so does the off switch.
That psychological shift is the central tension of ambient intelligence. We are moving from a paradigm of command where you explicitly tell a machine what to do to a paradigm of continuous anticipation.
Which requires a lot of trust.
It does, but the engineering solution to the privacy concern is edge computing. The audio of your doctor's visit isn't recorded, sent to a cloud database, and stored.
It's not.
No, the raw data is processed locally on the sensor right there in the room. The text insight is extracted, and the raw audio is instantly deleted from volatile memory.
So the data literally never leaves the room. That definitely mitigates the technical risk. But you're right, it requires an unprecedented level of implicit trust in the physical environments you and I inhabit. It feels like we are literally living inside the machine.
And the drive to eliminate friction between human intent and machine execution doesn't even stop with ambient sensors.
Well, it goes further.
The ultimate frontier of this convergence attempts to bypass physical interfaces entirely. No keyboards, no screens, no voice commands.
We are going straight to the neurology, which brings us to brain-computer interfaces, or BCIs.
This is where the convergence feels the most profound, honestly.
We are talking about establishing a direct, bidirectional, high-bandwidth communication link between the bioelectrical signals inside a human brain and a digital computing platform.
Right. To understand the leap here, you have to look at the physics of thought. When you intend to perform an action like moving your arm or forming a word, your neurons fire in specific cascading electrical patterns.
And historically, decoding that was nearly impossible because the brain is incredibly noisy, right?
And is a chaotic symphony of electrical static.
So how are we actually capturing and decoding that static now?
It relies on microelectrode arrays. These can be flexible polymer threads surgically implanted directly into the brain's motor cortex, or advanced non-invasive wearable arrays on the scalp.
And these electrodes pick up the raw bioelectrical voltage changes.
Yes, but the hardware alone is totally useless without the software. Advanced machine learning algorithms specifically trained on neural data are required to filter out the noise and identify the underlying pattern of intent.
So the AI translates the raw neural static into a clear digital command in real time, like move the cursor up, select this icon, type this letter,
The immediate proven applications of this are heavily medical, focusing on neuroprosthetics.
which is incredible.
For individuals suffering from severe paralysis, ALS, or spinal cord injuries, a BCI allows them to control highly articulated robotic limbs, navigate digital interfaces, and communicate at the speed of thought. It restores agency to those locked inside their own bodies.
It really is miraculous. But the source points out that the technology is rapidly moving beyond medical restoration. Research is laying the groundwork for high-bandwidth industrial and commercial applications.
Yeah, we are looking at a future of hands-free neural input in high-complexity work environments.
Like what?
Imagine an aerospace engineer manipulating a complex 3D CAD model, or a surgeon controlling microscopic robotic tools, purely through concentrated thought. It completely eliminates the mechanical latency of using their hands.
Okay, but think about the psychological implications of that for a second. We're talking about translating human intent directly into code. When you remove the physical act of typing or speaking, how does that change the way we actually form thoughts?
What do you mean?
Well, the physical delay of typing a sentence or speaking a word acts as an editorial buffer. It gives us a fraction of a second to evaluate our thought and filter it. If a machine executes my intent the exact millisecond it forms in my motor cortex, do I lose the filter of hesitation?
That is a fascinating question. It forces a profound evolution in human cognitive discipline. Users of advanced BCIs have to train their minds to interface with the machine.
So you have to learn the difference between a passing intrusive thought and an actionable command.
Exactly. It deeply blurs the boundary of where the biological self ends and the digital execution begins.
It is completely mind-bending. But if you step back, all of this, millions of autonomous AI agents negotiating complex workflows, humanoid robots dynamically processing physical physics, ambient intelligence analyzing real-time audio streams, and BCIs decoding the neural static of the human brain, it all creates a massive, brutal physical reality.
The sheer volume of data being processed every millisecond is unfathomable.
Which is exactly why the digital world is crashing into thermodynamics, like we said at the start.
Right.
The computation required for this ecosystem cannot run on the infrastructure we had 5 years ago.
No, not even close.
And this brings us to the bedrock muscle and the cryptographic shield required to sustain this age of abundance: computing power, quantum networks, and AI cybersecurity.
The text is explicit that the immense complexity of these frontier AI models has turned raw computing infrastructure into a global bottleneck.
Standard central processing unit CPUs are entirely inadequate for the math required by neural networks.
Right, because CPUs process tasks sequentially. They are great for running an operating system, but terrible at the massive parallel processing required to simulate intelligence.
So AI supercomputing platforms use fundamentally different architectures.
They merge traditional CPUs with massive clusters of specialized GPUs, and critically, application-specific integrated circuits, or ASICs.
And ASICs are chips physically hardwired to do one extremely specific mathematical operation at blinding speed, rather than being programmable for general tasks.
Exactly. And the most fascinating development the source highlights here is the scaling of neuromorphic computing.
Wait, neuromorphic?
Yeah, we are building silicon that physically mimics the biological architecture of the human brain. Instead of rigid logic gates, neuromorphic chips use artificial neurons and synapses.
Oh, wow.
They process information through spiking neural networks, meaning they only draw power when a specific signal fires, just like organic neurons in your head.
Which makes them orders of magnitude more energy efficient for AI workloads.
Totally. And the application of this supercomputing muscle is what actually drives deep tech. The text emphasizes that this isn't about generating text faster, it's about simulating reality.
Like in biotech.
Yes. Biotechnology firms use these supercomputing clusters to run deep molecular simulations, modeling how complex proteins fold. They can simulate billions of chemical interactions and discover life-saving pharmaceutical compounds in weeks.
Completely bypassing years of slow, trial-and-error wet lab experiments.
Or meteorologists using it to run hyper-localized, real-time climate models to predict extreme weather events with terrifying accuracy.
But even the most advanced supercomputers are bound by the limits of classical physics. The source introduces the true paradigm breaker next: quantum communication and computing.
This is the technology that transitions from the physics lab into commercial reality.
To understand the leap, you have to look at the foundational unit of data. Traditional computers run on bits, electrical switches that are either strictly 1 or strictly 0, binary.
But a quantum computer uses qubits. Through the principles of quantum mechanics, specifically superposition, a qubit can exist in a state of 1, 0, or a complex probability of both simultaneously.
And through quantum entanglement, the state of one qubit is instantly linked to the state of another, regardless of the physical distance between them.
Right, so the result is that a quantum computer doesn't solve complex problems by trying one combination after another, like a classical computer breaking a password. It explores virtually all possible combinations simultaneously.
So calculations that would take a traditional supercomputer millennia to resolve, like complex molecular modeling or prime number factorization, can be solved by a mature quantum computer in minutes.
Exactly. But that raw computational power creates an immediate existential crisis.
Because of encryption.
Yes. The encryption that secures the entire modern digital world, every bank transaction, every government database, every piece of proprietary corporate data, relies entirely on math problems that are just too difficult for classical computers to factor.
But a scalable quantum computer will slice through standard RSA encryption effortlessly.
It renders our current cryptographic defenses entirely obsolete. That is the threat.
Which is exactly why the text explicitly pairs quantum computing with quantum communication. The defense against quantum decryption is a post-quantum cryptographic shield, specifically quantum key distribution, or QKD.
And QKD is brilliant because it doesn't rely on complex math to secure data. It relies on the absolute laws of physics.
It transmits encryption keys using the physical properties of single photons of light.
Right. Think about the physics of that. In quantum mechanics, the very act of observing or measuring a quantum state permanently alters that state. This is known as the observer effect.
So if an eavesdropper tries to intercept the stream of photons to steal the encryption key, their measurement forces the delicate quantum state of the photons to collapse. The polarization of the light literally changes.
Exactly.
My analogy for QKB is that it's like sending a highly classified letter in an envelope that literally turns to ash the exact millisecond an unauthorized person's eyes look at it.
That is a perfect analogy. The receiving party instantly detects the anomaly in the photon stream, they know the channel is compromised, and they just discard the key.
It is physically impossible to steal the data without destroying it and alerting the network.
And that level of physical, hardware-based security is also driving the shift in how we process data in the cloud, leading to the rise of confidential computing.
Because right now, the cloud is inherently vulnerable.
It is. Traditional cybersecurity is relatively good at protecting data at rest when it's sitting on a hard drive and in transit when it's moving across the network.
But to actually run an AI model on that data, the server has to decrypt it into the system's active memory.
And the exact moment the data is unencrypted in the RAM, it is exposed. It's vulnerable to compromised operating systems, hypervisor exploits, or even a malicious administrator working at the cloud provider.
Confidential computing solves this by securing the data while it is actively being processed, not just at rest or in transit.
The mechanism here relies on hardware-level isolation. It uses trusted execution environments, or TEEs. A TEE is essentially a cryptographic vault built directly into the physical architecture of the CPU.
The data goes into the vault locks, and the data is decrypted, processed by the AI, and re-encrypted entirely within that isolated hardware enclave.
Not even the cloud provider or the operating system can see inside the vault.
This unlocks massive operational capabilities. It allows highly regulated healthcare networks or even fierce corporate competitors to pool their proprietary data into a massive shared cloud supercomputer to train a specialized AI model,
Mathematically guaranteeing that none of them can access each other's raw data. It creates perfect trust in a trustless environment.
And we desperately need that flawless architectural trust because the offensive capabilities of hackers are scaling just as fast as the defensive tech. The source notes that the era of reactive cybersecurity is dead. Human reaction time is simply too slow.
Hackers are increasingly deploying their own malicious AI tools to write polymorphic malware code that constantly rewrites its own signature to evade detection.
And autonomous agents that endlessly probe networks for weaknesses. If you are waiting for a firewall alert to trigger, you have already lost.
The paradigm shift here is preemptive exposure management and AI cybersecurity. Organizations are deploying automated AI-driven security platforms that operate on continuous
They
offense.
do not wait for an attack.
No, they run 24/7 using reinforcement learning to constantly simulate real-world adversarial tactics against their own infrastructure.
These systems map out intricate attack paths. They discover how a hacker could exploit a minor misconfiguration in an employee's laptop, pivot to a dormant cloud server, and string together multiple low-level vulnerabilities to eventually compromise the core database.
And then the AI discovers the exploitability path and autonomously deploys the patch, closing the door before a human adversary even launches the attack.
Okay, but if we step back and look at the reality of this, if hackers are using malicious AI tools, autonomously hunting for vulnerabilities,
Yeah.
and we are using automated AI security platforms, autonomously patching them at machine speed,
Yeah.
aren't humans essentially stepping out of the loop of our own security? Isn't this just an endless, invisible, machine-on-machine arms race playing out in the background of our civilization?
It is the stark reality of the deep tech era. Humans can no longer fight at the speed of the algorithm. Our role elevates from being the soldier on the battlefield to being the general who defines the parameters of engagement and the rules of the defensive AI.
We establish the governance, and the machines fight the war.
It's sobering.
Very. But all of this staggering computation, the neuromorphic chips, the quantum networks, the automated cyber defenses, requires an immense continuous flow of physical resources.
Which brings us to how we are physically rewiring the world to sustain this. Autonomous mobility, urban logistics, and next-generation energy.
Because the software intelligence we've discussed is finally mature enough to completely overhaul the physical supply chain. The text explicitly highlights that autonomous vehicles have crossed the critical threshold.
They are no longer confined to highly controlled, geofenced testing environments. Robo-taxis are operating commercially in major urban centers right now.
But moving human passengers is actually a secondary economic benefit. The true civilizational disruption is the automation of heavy freight and urban logistics.
We are talking about autonomous middle-mile logistics. Massive Class 8 autonomous trucks running continuous high-speed routes between major distribution hubs.
And these vehicles are fundamentally unconstrained by the physiological limits of human drivers. They don't experience highway hypnosis. They don't require mandatory rest periods.
And their sensor arrays provide 360-degree situational awareness in total darkness. They operate 24 hours a day, 7 days a week.
And once that heavy freight reaches the urban edge, the system hands the goods off to the last-mile logistics network.
Fleets of small, highly maneuverable sidewalk and bike lane delivery bots.
If you visualize the flow of goods, the autonomous middle-mile trucks are the major arteries pumping massive volume continuously across the country. And the last-mile sidewalk delivery bots are the tiny capillaries reaching right to your front door.
It's a great analogy.
But with supply chains becoming entirely automated and running 24/7, how drastically does this change the layout of our cities for the listener?
The economic impact of removing human labor costs and standardizing the speed of delivery completely alters urban planning. If logistics are perfectly automated and nearly instantaneous, the massive retail footprint in city centers becomes obsolete.
The city transitions into a purely residential and social space, while the invisible autonomous logistics layer operates continuously underneath and around it.
Exactly. But an entirely automated 247 global logistics network, combined with the massive power demands of AI supercomputing data centers, creates an insurmountable energy crisis if we rely on legacy storage technology.
The source pinpoints the exact bottleneck: standard lithium-ion battery chemistry.
The global push toward electrification has completely exposed the geopolitical and geological vulnerabilities of lithium, cobalt, and nickel supply chains.
There simply is not enough accessible material to power an age of abundance, and mining it is environmentally destructive and politically volatile.
So to shatter this physical constraint, the deep tech sector is scaling two radically different next-generation battery chemistries. The first solves the problem of massive grid-scale energy storage and short-range utility: sodium-ion batteries.
Yes, sodium. Literally the elements found in salt.
Yes, the geological abundance of sodium compared to lithium is staggering. It is thousands of times more common, entirely removing the geopolitical choke points of battery manufacturing.
And it's incredibly cheap to produce.
But beyond the economics, the chemical properties of sodium ion provide crucial operational advantages. Sodium batteries have vastly superior thermal stability.
Meaning they don't catch fire.
Right. They are highly resistant to thermal runaway, so they don't pose the catastrophic fire risks associated with damaged lithium-ion cells.
And the text notes they work better in the cold.
The ionic transfer mechanisms in sodium allow them to operate efficiently in freezing temperatures, where lithium batteries typically suffer severe degradation.
But sodium batteries are physically heavier and less energy dense, making them perfect for stationary grid storage to back up data centers or for heavy, short-range delivery bots.
Right, but for high-performance applications where weight is the ultimate enemy, the text points to the holy grail of energy storage: solid-state batteries.
Traditional lithium-ion batteries rely on a volatile, highly flammable liquid electrolyte to shuttle ions back and forth between the anode and the cathode.
And solid-state technology replaces that chaotic liquid with a structured solid material, often a specialized ceramic or glass lattice.
Explain the mechanism there. Why does a solid lattice completely change the performance profile of the battery?
Well, in a liquid electrolyte, as the battery charges and discharges repeatedly, microscopic metallic structures called dendrites form.
Wait, what exactly is a dendrite?
Basically, it's like a tiny, jagged metal spike that grows inside the battery. And if these dendrite spikes grow long enough to pierce the separator inside the battery, they cause a catastrophic short circuit and fire.
Oh, wow.
But a solid-state lattice physically blocks the formation of dendrites?
Because the dendrites literally can't pierce the solid ceramic structure.
Exactly. By eliminating the dendrite risk and the flammable liquid, you unlock two massive capabilities. First, you can safely push an immense amount of current into the battery, slashing charging times from hours down to minutes.
In second.
You can pack the active materials much closer together, effectively doubling the energy density.
So an electric vehicle can go twice as far on a single charge with half the weight. And crucially, that energy density threshold is exactly what makes commercial electric aviation viable. You cannot have autonomous logistics without the solid-state breakthrough.
But even with perfectly optimized solid-state batteries and infinite sodium grid storage, we eventually hit the ultimate hard limit.
The Earth itself.
Yes. The Earth is a closed thermodynamic system. It has a finite electrical grid, finite surface area for server farms, and a finite capacity to absorb the massive heat generated by advanced computation.
The AI models are getting too large. The data centers require too much water for cooling, and they draw too much raw electricity from local grids.
When the infrastructure demands of the digital world exceed the carrying capacity of the planet, the technology has to literally leave the planet.
This is the final frontier of the convergence, escaping Earth through orbital infrastructure.
We are looking at the aggressive commercialization of low Earth orbit, or LEO. The first step is completely re-architecting global communication through direct-to-device, or D2D, satellite connectivity.
Historically, connecting to a satellite required highly specialized, bulky hardware. You needed an expensive sat phone with a massive external antenna, and you had to have an unobstructed line of sight to a specific patch of sky.
It was technology reserved for maritime shipping or deep wilderness expeditions. But D2D completely dismantles that physical limitation.
Aerospace companies are deploying massive constellations of LEO satellites equipped with highly advanced phased array antennas.
These arrays use complex constructive and destructive interference patterns to focus radio waves with incredible precision.
They basically act as space-based cell towers that are sensitive enough to pick up the relatively weak cellular radio signals emitted by standard, unmodified consumer smartphones from hundreds of miles above the Earth's surface.
It entirely erases geographic cellular dead zones. Whether you are in the middle of the Pacific Ocean, deep in a rural agricultural zone, or navigating a disaster area where local terrestrial cell towers have been destroyed.
Your everyday smartphone maintains an uninterrupted broadband connection.
It guarantees that every human being, every autonomous truck, and every ambient sensor is permanently connected to the global intelligence network.
But bouncing signals off a satellite is just a routing upgrade. The true paradigm shift, the one that solves the terrestrial bottleneck, is space-based compute and AI orbiters.
The thermal dynamics of training and running frontier AI models on Earth are becoming economically and environmentally hostile. You have to build massive facilities, consume gigawatts of electricity, and pump millions of gallons of chilled water through the server racks just to keep the silicon from melting down.
So the aerospace sector is taking the heaviest computational workloads and launching the data centers directly into orbit. We are putting servers in space because the Earth is literally too hot and power constrained to handle our demand for AI.
Operating in the vacuum of space provides two profound physical advantages that completely bypass terrestrial limitations. First, an orbital data center has access to immense continuous solar energy.
Right, because above the atmosphere, there are no weather interruptions, no atmospheric diffusion, and depending on the orbital path, nearly constant sunlight.
It is infinite free power.
Doesn't that completely reframe the entire environmental conversation around artificial intelligence?
Absolutely. And second, the ambient environment of space provides the ultimate heat sink. You completely eliminate the need for massive, complex HVAC systems and cooling towers.
Because you rely on advanced thermal radiation techniques to dump the heat of the servers directly into the freezing vacuum of space. The environment cools the hardware for free.
These are AI orbiter satellites embedded with high-powered neuromorphic and ASIC hardware.
So instead of a traditional satellite capturing multi-terabyte files of raw, high-resolution geospatial imagery and beaming that massive payload down to a ground station in Virginia to be analyzed,
The satellite analyzes the data in space.
the AI model runs right there in orbit.
It processes the agricultural data, the military intelligence, the maritime shipping routes instantly. It extracts the necessary insight, like here's the crop yield prediction, or here's the unauthorized vessel.
And it beams down a few megabytes of actionable answers instead of terabytes of raw noise. It drastically reduces the bandwidth requirements of global networks.
It is the ultimate testament to the convergence we've been discussing. The lines separating aerospace, thermodynamics, advanced silicon, and artificial intelligence have officially dissolved. They are a single, interdependent ecosystem.
And that synthesis brings us right back to the core premise of Paramendra's 2026 text. We started by looking at the evolution of intelligence, multi-agent systems autonomously negotiating workflows, and DSLMs providing flawless specialized execution.
We saw how those intelligent systems utilize generative AI native platforms to rapidly construct and deploy their own software architecture, completely upending traditional vibe coding.
We watched that software cross the barrier into physical reality, bipedal humanoid robots dynamically navigating human infrastructure because it's cheaper than rebuilding stairs.
Real-time translation hardware seamlessly bridging language gaps without lag. Ambient intelligence invisibly anticipating our needs in hospitals and homes.
We explored the ultimate biological convergence. Brain-computer interfaces directly linking human neural intent to digital execution. We broke down the massive infrastructural muscle neuromorphic supercomputing, unbreakable quantum cryptography, and autonomous AI cyber defenses required to sustain all of it.
And finally, we tracked the physical supply chains, the continuous flow of autonomous middle-mile logistics, powered by the breakthrough physics of solid-state and sodium-ion batteries.
Allowing this massive computational web to literally launch itself into orbit to find the boundless energy and thermal relief it requires.
This sweeping, interconnected architecture is what the source defines as the engine for the age of abundance. It is not a series of isolated gadgets. It is a fundamental rewiring of civilization's infrastructure.
We have thoroughly exited the era of simple, weightless digital apps confined to screens. We are living in a heavy, physical, deep tech reality. And for you, listening right now, this is an abstract science fiction reserved for the end of the century.
Not at all.
These converging forces are actively reshaping the trajectory of your career, the physical layout of your city, the privacy of your home, and the very nature of human interaction right this very moment.
The transition will be intensely disruptive, but the destination outlined in the text points toward a massive reduction in friction and scarcity.
But it leaves us with one final, deeply provocative question, a thought we want you to carry with you after this deep dive ends. We started this journey by talking about the heavy physical demands of this technology. We've seen how massive the machinery of abundance truly is.
The logistics and computational effort required to sustain it are monumental.
If we truly are entering this prophesied age of abundance, a world where multi-agent AI writes our software flawlessly, where humanoid robots and autonomous trucks run our heavy logistics 24/7, where ambient intelligence optimizes our physical environments without being asked, and where computation draws infinite energy from the sun in orbit. What happens to the human drive?
When the struggle for basic productivity and logistical survival is entirely solved by autonomous infrastructure, what does it mean to be productive?
When the machine removes the friction of daily existence, what will you choose to do with your incredibly valuable, truly weightless time? Keep questioning, keep looking closely at the edges of what's possible, and we will catch you on the next deep dive.